All right, good morning or afternoon, whenever you get around to watching this. Today, what we're going to go through is the concept of matrices. So, kind of what a matrix is, and then how to operate matrices and how to find the inverse of matrices and all that kind of fun stuff, and transposition and etc. So then that's all we're going to do today, and then eventually we're going to put these into civil engineering type problems. So matrix is basically something that looks like this, and it's an array of numbers. What that means is each number corresponds to some sort of value, but the whole system is linked together. The way we talk about matrices is rows and columns. So I represents the number of rows and J represents the number of columns. So rows and columns, just like Excel. And actually we can use Excel later on to start helping to solve some of these. And we denote it by the kind of, we denote a matrix by the number of rows and columns. So when we're talking about it, this one would be a 3x2 matrix, and this one is a 2x3. So 2 rows and 3 columns. It's probably unnecessary, but 2x3. So in civil engineering applications, we can use matrices in relation to structural analysis and as well as regression analysis. Structural analysis gets a little bit complicated. There is a post-grad course that we teach here at RMC and from the Mech Eng department that talks about matrices for structural analysis, because it's kind of the backbone to certain computer-aided finite element analysis programs. So I can go through examples, but we're going to just stick with matrices for right now and just keep talking about them. So there's a bunch of different types of matrices that we're talking about: row matrix, column matrix, square matrix, diagonal matrix, symmetric matrix, null matrix, and the identity matrix. So a couple of things that we're going to be using, we're definitely going to be using the identity matrix. We're not going to try to use all square matrices, but the identity matrix is something that's going to come up again. You just know that you have these in your notes here, and if I bring up different types of matrices in a row or column, you can always backtrack and talk about these numbers or these types of matrices. We can say that a matrix is equal when all numbers or all elements, all entries in the array or entries in the matrix are identical. So if in this case, we have A equals B because every single number is identical. If that's not the case, if even one number is off, then they're not equal. It should be relatively straightforward. When we do addition and subtraction, we have to do them in order. So if we just say that we have a matrix A, which is equal to A11, A12, A21, A22, and then we have a matrix B in the same order and of the same order is basically what I'm trying to say here. B21 and B22. I can add and subtract these because they're a 2x2 matrix, right? So that's 2x2, that's a 2x2. If I don't have the same type of matrix, then I can't add or subtract them. And when we're adding or subtracting A plus B, this is pretty straightforward. This one's a lot easier than multiplication. The entries are going to equal to A11 plus B11, A12 plus B12, A21 plus B21, and A22 plus B22. So really, it's relatively straightforward. If we want to do that with real numbers, what we're going to get is, let's just say 1, 8, 3, 4, 7, 2 plus 6, 9, 8, 5, 12, 3 is going to be equal to, well, we got 1 plus 6, so 7, 8 plus 9 is 17, 3 and 8 is 11, 9, 19, 5, right? And no different with subtraction. So again, we've got a 3x2, a 3x2, and it spits out a 3x2 matrix. We do the same with subtraction. Oops, that should be 1 and 4, not 1, 4. So I've got 3 minus 2 is 1. 1 minus 0 is 1. 4 minus minus 1 is going to be 5. 6 minus 6 is 0. Negative 7 minus 2 is negative 9. And 2 minus 1 is 1. So it's relatively straightforward. Addition and subtraction are nice and easy. Unfortunately, we're not going to do a whole lot of that. So I went through the examples already, actually, so I'm not going to bother with that. There's different types of multiplication when we talk about multiplication of matrices. Scalar multiplication is where we take a number or a variable and we multiply it by the whole matrix. So in this case, if we have this x and we multiply it by the matrix, then we're going to end up with the result there. If we want to do matrix multiplication, however, there's a couple rules that have to be followed. So they're listed right there. But basically what it looks like is those rules, and I'll go over them. We say that A is equal to this. And X, matrix X, is going to be equal to this. Then what we're going to get, I'm going to set it C, sorry, is equal to this. What we can do is we can multiply matrices if the number of columns in the first matrix must be equal to the number of the rows in the second matrix. So in this case, we have a 2 by 2. In this case, we have a 2 by 1. So these two numbers are equal, therefore I can multiply them together. What the resultant will be is going to be these two numbers. So the resultant matrix will be that. So if in terms of C, or A times X, if I get A11, A12, A21, A22 times X1, X2, what it's going to look like is, we'll say that equals C just for argument's sake. It's going to be A11, X1 plus A12, X2 plus A21, X1 plus A22, X2. So what we're doing is we multiply this number by that number, this number by that number, and that becomes our first entry in the series here. So that's this entry. And then we multiply this, and then we just multiply this one down by that one, and that becomes the second entry in our series, and we add them together. So for example, with numbers, if we say that D is equal to 1, 3, 5, 2, 4, 6, and E is equal to negative 7, 8, negative 9, 10, 11, 0. I've got a 3 by 2 and a 2 by 3, or sorry, 2 by 3 and a 3 by 2 rows times 3 columns and 3 rows times 2 columns. We can multiply that together, so these two are equal. So yes, we can multiply them. We get that D times E is going to be equal to, I'm going to write this big. We're going to end up with a 2 by 2 matrix, right? It's 1 times negative 7 plus 3 times 8 plus 5 times negative 9. That's the first entry. The second entry is going to be 1 times 10 plus 3 times 11 plus 5 times 0. And then we go down to the bottom. So we know it's a 2 by 2, so I'm going to just have an entry here. Actually, I'm going to erase this, make it a little bit smaller so I can put the final answer down below. 2 times negative 7 plus 4 times 8 plus 6 times negative 9. That's the first entry. And then I've got 2 times 10 plus 4 times 11 plus 6 times 0. And that whole thing is just going to equal negative 28, 43, negative 27, and 64. And that's matrix multiplication. So the rules again up here is how we do that, basically checking to make sure we can multiply them, figuring out what the resultant matrix looks like, and then multiplying each row by each column, kind of like I've just gone through in that example. Something about matrix multiplication is that it's associative, so that means that A times B times C is going to be equal to A times B times C. So you got the parentheses there. It also means that, I need to double check my notes. A times B plus C is equal to A times B, which is equal to A times C. Yeah, actually, I think that's plus. That should be plus. But they're not commutative. So A times B does not mean not equal B times A, which is, you can kind of, if you look at it the way that it, that we talked about it. So if we have if we were up here and we had a 2 by 3 and a 3 by 2, it's not going to end up being the same thing. So if we multiply E by D, we get a 3 by 2 and I'm just going to put little brackets there, and a 2 by 3. So they're going to be, we can still multiply them out, but now it's a 3 by 3 matrix and not a 2 by 2 matrix. So it doesn't have the same answer. If we want to transpose a matrix, it's denoted by whatever the matrix is with a little t at the top, so transposed. And basically all we're doing is interchanging its rows for its columns. The determinant of a matrices is something that we're going to use, and it's something that we can use to solve linear, homogeneous, and non-homogeneous sets of equations, which is useful sometimes. And basically the determinant is calculated by those two multiplied by each other, and then those two multiplied by each other. That's a little bad drawing. Those two subtract that. So yeah, we can use it to invert matrices. We can use it to determine a whole bunch of stuff with matrices. Gets a little more complicated in a 3 by 3. Actually, a lot more complicated in a 3 by 3. So the first term here is just going to be the diagonal multiplied by each other. The second term is these two here. Maybe I should do this in a different color. These two here multiplied by this one. The third term is a little bit more complicated. A11, A23, those 2, 3, and A32. And then we can keep going on, but it's a little bit more complicated. There's not really an easy way to kind of memorize it aside from just kind of taking a look at what happens, and then or memorizing that kind of thing, or having that in your notes. We're running out of colors here, and then A13 multiplied by A22 by A31. So it kind of goes all over the place there. But just note that it's right here in the notes, how to do the determinant for a 3 by 3 matrix. When we can also use minors and cofactors to find the determinant. So it's a little bit easier way of, instead of just memorizing this, we can actually do something that's kind of methodical. And it's a little bit cumbersome. It's a little bit cumbersome without the help of computers. But what we want to talk about is the idea of a minor. A minor, when it gets too large, a minor of a matrix is resulting by removing one row and one column. So if I want the minor 1, 1 of A, all I do is I remove this row and this column because it's going to be A11, right? So anything, the row and the column that's associated with. If I want the minor of A12 or M12, I'm just going to remove that row and that column, and then I can calculate the determinant of those, which we can use in order to get the determinant later on. I'll show you this here. Oops, should I remove this because it's from the other notes that I was using. So the cofactor is basically the minor of whatever area we're looking at times -1 to the number of rows plus the number of columns. So C11 is just minor 1, 1, m1, 1, times negative 1 to 1 plus 1, right? So that's 1 plus 1. The cofactor 1, 2 is equal to the minor 1, 2 times negative 1 times 1 plus 2. So it equals negative 3. What we can do with the cofactor is we can actually use it to calculate our determinant. And how we can do that is we can calculate the determinant for a certain row and for a certain column, and then we can actually use that to calculate the determinant or the inverse for a matrices. So what we can do in this case, the determinant of A is going to be equal to the determinant of 1, 2, negative 4, 3, 1, negative 2, 4, 2, 3. So if we say that our determinant is going to be equal to A1, 1 times the cofactor 1, 1 plus A1, 2 times the cofactor 1, 2 plus A1, 3 times the cofactor 1, 3. What we can get is we can actually calculate our determinant. So C1, 1 is going to be equal to negative 1 to the power of 2, right? 1 plus 1 times the determinant of the minor. So in this case, if we get rid of 1, 1, it's going to leave us with 1, negative 2, 2, 3. And that's going to be equal to 7. Cofactor 1, 2 is going to be equal to negative 1 to the 3, which is going to be 3, negative 2, 4, 3. And that's going to be equal to negative 17. And the cofactor 1, 3 is going to be equal to negative 1 to the fourth power of 3, 1, 4, 2. And that's going to be equal to 2. So the determinant of A along that column, A1, 1, is going to be 1 times 7 plus 2 times negative 17 plus negative 4 times 2. And that's going to be equal to negative 36. So it's something that we can use, and I'm going to go through a little bit more of a specific way to use the cofactor lately, but as long as you understand what the cofactor is and you understand what the minors are, then we're good to go from this one. And then it can be used to help determine the determinants at some point. So there's a couple special properties of determinants that we need to talk about. If there are any two rows or columns that are identical or a scalar multiple of each other, so in this case row 1 and row 3 is equal to 2 times row 1, then the determinant is 0. So that's kind of handy to know. If we interchange two of the rows or columns in the matrices, we get the opposite sign. So the determinant of this matrix here is 8, and if we interchange these two, or negative 8, sorry, if we interchange these two columns, then we're going to get that it's 8. So if we know the determinant of one matrix, it looks like this, we can use it to know that the determinant from another one. If we transpose the matrix, however, the determinant of that matrix is equal to the determinant of the transposed matrix. And if we factor out something from a matrix or multiply it scalarly, the determinant will be multiplied by the same scalar, right? So in this case, I had, or for any column, sorry, any common factor for any column, I have 2, 1, 4, so 2, 4, 6 here. I took out the 2 from here, multiplied it out, and it's going to be equal to that. It's going to double the determinant of that matrix, and then it's going to be equal to the same thing. And then the determinant, it remains unchanged if any one value, if anything is subtracted from another. So in this case, I took row 1, and in row 2, I took row 2 minus row 1 in here, and then the determinant is the same. So matrices don't divide. Instead, we multiply it by the inverse of the matrix in order to do division. One of the properties of the inverse of a matrix is that we multiply a matrix by the inverse of its own inverse. We get the identity matrix, right? So that 1, 0, 0, 0, 1, 0, or whatever, how many ever rows and columns we have the identity matrix, as long as all the diagonals are 1. It can actually be really useful because it'll help us solve a system of equations. So if we say that A is equal to x plus y, so something we could have something like this. So A1, 1, A1, 2, A2, 2, 1, A2, 2. So that's matrix A times x, x1, x2 is equal to y1, y2. We can actually use that property of the inverse to solve for our values of x. And we're going to go over 2 of the methods to solve for the identity matrix. First one is called Gaussian elimination. Basically, we transform the original matrix into the identity matrix by doing multiplication, addition, subtraction of rows and columns and factors of rows and columns. And we do the same to the identity matrix, and then what started as our identity matrix ends up being the inverse. So if we say that we have a matrix A, which is going to be equal to 3, negative 3, 5, 1, 2, negative 6, 2, negative 1, 3. So that's our original matrix. I want to find the inverse of A. So I'm going to write down my identity matrix over here. And now I'm just going to start trying to solve. I'm going to try to turn the original matrix into the identity matrix. So this one here, I and A into I, and then whatever is left on here by doing the same multiplication and division is going to be our inverse matrix. So first thing I'm going to do is I'm going to take R1 and divide it by 3. The reason I want to do this is because now I can have my 1 here. For my identity matrix, I've already got 1 solved, and I'll show you why that's important in a second. So I'm going to get negative 1 and then 5 over 3. That leaves me 1, 2, negative 6, 2, negative 1, 3. But now I'm going to do the same to the identity matrix. So I got 1 over 3. All right, so that's part 1 done. So now what I want to do is I want to keep moving down, and I want to start making zeros and ones as much as possible. So what I'm going to do is I'm going to take R2 minus R1, and then I'm also going to take R3 minus 2R1. So now what I'm going to do is I'm going to zero out this column here. So I got 1, negative 1, 5 over 3, 0, and then time minus R1, so that's going to be 3. And this one works out to negative 23 over 3. This is 0, and I've got 1 and negative 1 over 3. Now I've got to do the same with my identity matrix. And then 0, 0, 1, 0, 0, 1. Right? So now I'm going to take R2 and divide it by 3. And what I'm doing is I'm making all these zeros, and now that they don't affect if I have to go up and down, multiply anything up and down, I've got that whole column sorted out, right? So I'm going to be left with 1, 0, 0, negative 1, 1, 1, 5 over 3, negative 23 over 9, and negative 1 over 3. In this case, I got 1, 3, 0, 0, negative 1 over 9, 1 over 3, 0. So now I could use my row 2 to get rid of this 1 in row 3. So I'm going to go to row 3 minus row 2. And I'm going to end up with 1, and then 0, 0, and then 20 over 9. And then this one, where am I at? Negative 5 over 20. Negative 9 over 60. Oh, no, sorry, I'm jumping ahead of myself here. Negative 5 over 9, 1 over 3. And that's 1. So all I'm doing is I'm trying to turn this one into my identity matrix, right? So now I'm going to take row 3 times 9 over 20. Right, and now I'm left with 1, negative 1, 5 over 3, 0, 1, negative 23 over 9, 0, 0, 1. So now I've got my diagonal of all ones, and now I'm going to try to figure out how to get rid of the other numbers here in just 1 sec. And that leaves that's negative 5 over 20 when it simplifies, negative 9 over 60, and 9 over 20. Continuing on, I'm going to go back up now, and I'm going to take R1 plus R2, so I'm going to get rid of that. That 1 and negative 1 there, so I got 1, 0. And it was important to get this column because now every time I multiply anything or add anything on my way up, I'm not going to change anything drastically. That leaves me with negative 8 over 9. 0 and 1. And now oh, and I'm sorry, I'm going to R2 is equal to R2 plus 23 over 9 R3. So all I've done is I've simplified it again. And I forgot to write that step down. Just trying to keep track of my identity matrix here and what it's turning into. Negative 5 over 20, negative 3 over 20, 9 over 20. And then I'm just going to take R1 and make it R1 plus 8 over 9 R3. And that gets rid of this. So now I've got the identity matrix left on this side. And then I've got some giant matrix over here that makes things a little bit more complicated. This is going to end up 0, 1 over 5, 2 over 5, negative 3 over 4, negative 1 over 20, 23 over 20, negative 1/4, negative 3 over 20, and 9 over 20. And now what this means is that this here is our inverse matrix. So that's one way of doing it. You can see it's a little bit cumbersome and it requires a little bit of trying to figure everything out and keeping track of things. So kind of a lot of room for error in this one. But basically what we can do, we can use that. It's a really powerful tool because if I have something like this, where I've got my A times X plus Y. So in this case, let's just read off the first row here. It would be 3 times X1 minus 3X2 plus 5X3 is equal to 4, right? So all those together is one equation. So I have 3 equations, a system of 3 equations here. If I can just quickly find the inverse of A, I can actually find the values of X that work for all 3 of those equations in order to solve for those systems of equations. So as you can see here, we find our inverse, the inverse of what we just found. We multiply that out, and our values of x1, x2, and x3, respectively, are equal to 1, -2, and -1. So it's something, once we find our inverse, it's actually quite powerful to use to solve for these systems of equations. Another method that we can use is a little bit cumbersome and tedious, but both ways are kind of cumbersome and tedious, but it helps to have a computer in order to solve for this one. But what we can get is we're going to look for the cofactor matrix. So what we do is we take the cofactor of each of these spots, so C11, C12, C13, and we input it into its own matrix here. So wherever C11 is, it becomes the cofactor matrix. Then we use the cofactor matrix to find the adjoint matrix, which is the transposition of the cofactor matrix. So we turned our rows into columns. So row 1 becomes column 1, and then so on and so on. And we can use that the inverse of A is the adjoint matrix times 1 over the scalar for the matrix. So we determine the determinant, 1 over the determinant. We determined that the determinant was 20. We multiply that by the transposition of the cofactor matrix or the adjoint matrix, and we end up with the same thing that we ended up with by doing it the other way. So the longest part of this one is finding your cofactors. So C11, C12, C13 is finding all your cofactors, plugging them into that matrix, but then you can just transpose it and find the determinant of the original matrix A and multiply it by the adjoint matrix. So 1 over the determinant is equal to the 1 over the adjoint. 1 over the determinant times the adjoint matrix is equal to the inverse matrix. So it's a little bit more straightforward rather than going through and trying to just do matrix manipulation in order to get it the way we did it here. There's a lot of steps here. It's methodical as long as you keep everything straight and finding common denominators and all that stuff. Typically the side of my page over here would look like a mess because I'd be doing common denominator work all the time. But if you keep it straight, it's relatively straightforward. This way, the hardest thing to do is either calculate out the determinant. If the matrix becomes more than 3 by 3, it becomes really hard to calculate the determinant. And then just plugging in numbers to solve for the cofactor matrix. But other than that, it's not too bad. So we'll end up using both ways later on in the course. I just wanted to go over both ways. The inverse actually does have a few different properties as well that are unique to the inverse of the matrix. The inverse of the inverse matrix is equal to the original matrix, which is good to know. If we have a matrix A multiplied by matrix B and we take the inverse of that resultant matrix, then we can actually take the inverse of B and the inverse of A and multiply them together, and it becomes the same thing. The inverse of even 3 matrices multiplied together is their individual inverses multiplied by each other. And then the transposition of the inverse matrix to the transposition of the inverse matrix is equal to the inverse of the transposed matrix, if that makes any sense. That's all I have for today, so that should cover our matrix review. What we're going to see next time is how this applies to civil engineering. So we're going to use an example and go through the matrix manipulation for an actual example. So how to come up with a matrix for a civil engineering application, and then how to solve it. That's all I have for you guys today. Stay tuned for further information, and we'll talk soon.